we're going to take the region bounded by y equals square root of x and y equals x, and we're going to do this several different ways. We're going to the first problem, we're going to rotate about the x-axis. So the first step is for us to graph the equations and figure out what the region is. Good first step would be to see what the point of intersection for the two. So setting square root of x equal to x. To solve this, I square both sides, and I get x is x squared, and I get x minus x squared is 0. X gets factored out. 1 minus x is 0. So I have two x values where the two curves intersect. One is x is 0, the other is x is 1. And because y equals x, it means the y value will be the same. I'm now going to graph. Y equals square root of x looks something like this. It's half of a parabola to the right. And I found that these intersect at 0, 0, and 1, 1. So y equals x is here, and the point of intersection here is 1, 1. The initial one is 0, 0. This is the region that we are dealing with. This is the region we are going to rotate about the x-axis. I put in the typical rectangle, and we notice that that typical rectangle has to be perpendicular to the axis of rotation, and because it's not on the x-axis, it is a washer. So now I identify capital R and little r. Capital R is the y value on the curve y equals square root of x, so it's square root of x. Little r is the y value on the line y equals x, so it's just x. From that, I know that the volume will be pi, and it's a washer, so it's difference of squares. And sure enough, the capital R is square root of x, little r is x, and this was between 0 and 1. And that is the setup for the volume of that solid of revolution. And I'm going to write etc. because we can go on and finish this by squaring and then getting antiderivatives, but we won't do that now. We're just setting it up. Now, as a second problem, I'm going to take that same region, and it's going to be rotated, this same region. I'm going to rotate about the line y equals negative 2. To see how this is going to be, I'm going to graph it again. We graph y equals square root of x, y equal, my line looks a little curvy there, it shouldn't be, y equals x. We now have that region, but now I put, and this isn't to scale, the line y equals negative 2. Putting in the typical rectangle, we're now going to take that rectangle and rotate it around that line y equals negative 2. I just drew the washer, and now look what happens. We have that the larger radius is from negative 2 up to the higher curve, which is square root of x, and the lower radius, the smaller radius, r, is there. We have to identify what is capital R, what is little r. Capital R is the upper y value minus the lower, so it's square root of x minus a negative 2, which becomes square root of x plus 2. The lower one is the y value on the line y equals x minus a negative 2. X minus a negative 2, which is x plus 2. So rule of thumb, to get a vertical distance, it's always upper minus lower. Now we're ready to set up the formula for the volume. So it's pi, and it's going to be difference of squares. And the larger r, can everyone see, is square root of x plus 2. The smaller radius, which is the radius of the hole, is x plus 2. And of course, just like the other one, this was between 0 and 1. And of course, I'll say etc., you would have to FOIL radical x plus 2 and x plus 2, work it all out, and you're going to get a value. So now, as a third problem, we're going to take the same region, only this time what I'm giving as the axis of rotation is we're going to rotate about the line y equals 3. And I'm going to go to the next page to get an actual diagram of that. We're going to graph that same region. We've got y equals square root of x. We've got y equals x, and we know it's 1, 1. We've got that same region. So this isn't to scale, but let's say here is the line y equals 3. So I'm going to put the typical rectangle. I'm going to put two distances. From 3 to the bottom edge is little r because it's smaller. From 3 to this edge is capital R, because those are being rotated about that line. So whichever distance is smaller is the smaller radius. We're now going to write down what capital R and little r. Capital R is 3 minus the y value on the line, which is 3 minus x. Little r is 3 minus the y on the curve, which is 3 minus square root of x. So now we're going to put the integral for the volume, and because it's a washer, it's pi difference of squares. It's dx because the verticals, rectangles, and it was from 0 to 1. The first parentheses gets capital R, the second little r. And of course, I'm going to write etc., but you're going to FOIL and you're going to combine like terms and you're going to get the answer. So now we're going to do the same region, only now I want to do that same region, but you're going to rotate about the y-axis. Let's take the diagram. We have the xy coordinate system. We graph y equals square root of x, y equals x, and it intersects at 1, 1. This is our shaded region. Because it's about the y-axis, I subdivide from 0 to 1 on the y-axis, and that gives me a horizontal typical rectangle. With this one, this distance to the bottom edge is little r. Right here is capital R. We now define capital R and little r. Capital R is the x value, but it's the x value on the line. It has to be in terms of y, a function of y, and that's y. Little r is the x value on the curve, but y equals square root of x. I have to solve for x. I square both sides and I get x is y squared. So little r is the x value there, which is y squared. Now, because it's a washer, because the rectangle isn't on the axis of rotation, we get volume is pi the difference of squares. Only this time, because it was on the y-axis, it's delta y or dy here. Capital R is y, little r is y squared. And again, in this case, we're going from 0 to 1. I write etc. because the last step would be for you to do the algebra and get the antiderivative.